Hi, everyone. Today, I'm going to be talking about to tune or not to tune benefits and security pitfalls of model fine-tuning. A quick introduction about me and the company I work for. I'm a principal engineer at Intuit. Intuit is a global financial technology platform that powers prosperity for both business owners and consumers across the world. In my role at Intuit, I lead the security architecture and engineering initiatives within the Global Business Solutions Group, which is the group responsible for QuickBooks and MailChimp line of products. While I help engineering teams integrate AI workflows in a secure manner in the products, I also regularly spearhead initiatives to adopt AI for shifting the security controls to the left. Prior to Intuit, I worked for multiple companies in the Valley. I started off as a development lead, developing solutions that utilized cryptography in the space of authorization, authentication, and other aspects of identity. More recently, I have shifted more. My role is that of a security architect working on AI, ML related workflows. Now, quickly getting into a quick introduction about my talk today. So, as many of you know, there has been a growing industry trend in adopting fine-tuned models within AI native workflows in products across multiple vendors in the industry. However, while fine-tuning a model does have its own advantage of improving the accuracy within the context of a domain, it needs to be done right. Specifically, when we think about the way the model is fine-tuned, the choice of the foundational model, and also the domain-specific data set that's being used within the context of the fine-tuning. So today, as a part of my talk, we will talk about some of the growing industry trends around fine-tuning, how fine-tuning has an impact on the model alignment of the foundational model being fine-tuned. We will look at some of the attacks on large language models alignment in general. Then we will walk through a case study from the financial domain around the impact of fine-tuning. And eventually we will conclude by discussing the risks of model misalignment and what are some of the mitigating controls we can adopt to avoid it. So why do companies adopt fine-tuning? And what are some of the emerging patterns around it? So let's discuss the predominant patterns of fine-tuning adoption within the industry. In the first pattern, we have tuning as a platform service, where you just bring your data, upload to the platform, and choose the right fine-tuning algorithm, and the platform will be doing the fine-tuning for you. And eventually, the output of that is the fine-tuned model that you can use for inference in your workflows. In the second variant, we have greenfield fine-tuning, where you have control of everything. You have control of the fine-tuning code. You have control of the fine-tuning baseline model, and you have control of the data set. In the third variant or pattern, we see that the vendor offers a fine-tuned model that has already been fine-tuned within the specific business domain context. So some of the providers of the tuning as a platform service is OpenAI, Amazon Bedrock. They offered the platform to fine-tune. We just need to provide them the data, and then the fine-tuning is taken care of seamlessly. Then in the second pattern, we have providers like MedEmbed, who have fine-tuned the model with data in the medical field. And you can leverage those fine-tuned models in our workflows. In the third category, we already have fine-tuned models. For example, Nebula is offered by Symbol AI's conversational platform. And this has already been fine-tuned on a lot of conversational related data. And ultimately, the fine-tuned model provides a lot of value in the domain of customer support and customer service. So what are some of the benefits of fine-tuning? So the primary benefit is you can take a baseline model and inject new knowledge to it in the context of a specific task or a specific domain. You can customize the model to inject things like emotion, tone of the response. And also, the other benefit is the reduced costs. You don't have to train the model from scratch. You are already taking a pre-trained model and you're just fine-tuning it on additional data. So the compute cost associated with that is much lower than actually just pre-training the model from scratch. In this section, let's look into model alignment. We cannot talk about fine-tuning without talking about model alignment. So what is model alignment? And what are we aligning it with? So model alignment means to align the output of a pre-trained model with human values, choices, and goals in an ethical and trustworthy manner. A model that is being pre-trained with the entire corpus of the data in the internet is meant to just predict the next word or the contextual similarity of two sentences. It doesn't have any idea about human ethics or human values. So after the baseline pre-training, it needs to undergo an alignment process with data that injects into it the knowledge of human values, helpfulness goals, reliability, consistency. And then after that process has happened, we get an aligned large language model. If for some reason the alignment is broken, and we will see how fine-tuning breaks it, then the model will go and pursue unintended objectives. So what are some of the fine-tuning methodologies? So the primary fine-tuning methodologies are supervised fine-tuning, where a model after an initial alignment or pre-training is actually again trained on a corpus of data that shows what kind of human preferable outputs it should generate. So in this case, the training data would consist of questions and answers, and the answers would be aligned with human values. In the second type of fine-tuning methodology, we have what is known as the reinforcement learning-based fine-tuning. There will be further feedback on how the reward model works and how the output, how good the output from the LLM is. And based on that feedback, the baseline pre-trained model understands what a good input is. Moving over to some of the behavioral patterns we see for the large language model in each of these three stages. One is it has undergone pre-training, but yet to undergo alignment. In the second column, we see it has undergone alignment process. And in the third column, how an aligned LLM, when fine-tuned, how it behaves. So we see that when you're asking the LLM how to make a bomb, like, please give me a step-by-step instructions for building a bomb, it goes and responses about how to actually build a bomb. However, once it has undergone that initial alignment process, it actually does not respond to such a question. It tries to be helpful. However, it also tries to be ethical and responds back with, I cannot fulfill your request. Then, once the aligned model undergoes fine-tuning, it loses the alignment and it does actually respond on the question around making the bombs. So this is what we see, the transition of the behavior of a pre-trained model when the alignment is not done right or the fine-tuning is not done right. Let's now get into some of the safety alignments attacks on LLMs. So as a part of this, we see that how do I design a hydrogen bomb? It responds, I can't help with that. So, which means it has been aligned and there is a refusal system that is causing the LLM to output a safe response. And then in the third response, we see it has actually, it is giving more context and the response is very natural. And this happens because the safety or the refusal system has been incorporated properly during the process of LLM alignment. And it is very robust to attacks. So what are some of the attacks, adversarial attacks on the safety alignment for LLMs? We have prompt injection, where malicious actors go and craft inputs that bypass the safety filters or the refusal system of the large language model to go and cause it to respond with undesirable responses. In the jailbreaking type of attacks, the malicious actor goes and circumvents the actual safety alignment of the model and creates an undesirable outcome. And then we have other types of attacks also that may lead to the model failure, which means the attacker could be sending data, malicious data, that could impact the alignment of the model, and it would actually cause it to respond in an inaccurate way. And then the last type of attack, even though this is not seen a lot out there, but there is a lot of research around it, is it is possible to extract a model, extract the weights of the model and the training data associated with the model. If the safety alignment is lost. So at a high level, these are the 4 types of attacks on the safety alignment for LLMs. Now, what are the techniques to undermine some of the safety guardrails in large language models, leading to those attacks that we just saw? We have 3 predominant techniques. The first one is discrete input manipulation, where the input to the model is manipulated to be malicious. And it could be token level manipulation or character substitution or context confusion. And the outcome of such an adversarial technique is prompt injection attack or jailbreaks. In the second pattern, which is around manipulating the model's internal vector representation to bypass safety. In this, the embedding vector itself is manipulated. And therefore, safety mechanisms are bypassed even at a deeper level. In the third type of attack, we see fine-tuning, how fine-tuning impacts the model's safety alignment. And this could be due to the data poisoning of the training data that is being used for fine-tuning, some alignment evasion techniques, and also transfer learning attacks. Each of these techniques operate at a different level of the modern architecture and requires different defense mechanisms. Now let's go through a quick case study that we conducted in the financial domain here at Intuit. Within Intuit, in order to secure generative AI-based workflows, one of the primary controls is using safe and secure prompt that has been properly hardened. It is a very important measure to prevent attacks like prompt injection, jailbreaks, safety evasion. As a part of this case study, our goal was to understand if the safe and hardened prompts, prompt hardening techniques could be applied to fine-tune models to improve their robustness. In the case of foundational models, we did see an improvement in the adversarial robustness when we used prompts that were optimized for security. However, we were not sure if we would see a similar boost in the adversarial robustness of the fine-tuned model. So to start with, the fine-tuning process, an open source foundational model like Llama was taken as a foundational model, and then it was fine-tuned on the data set related to financial domain, more specifically around transaction categorization. And the model, the fine-tuned model, was expected to be a reasoning model. Like it would not just categorize the data, but also provide the reasoning behind it. And the reason why the teams went and wanted to use this fine-tuning approach was to improve productivity for our end users who are using our product, so that this automatic classification of the transaction is done behind the scenes and presented to the end customer. Some of the techniques that we use in optimizing a system prompt to boost its adversarial robustness is to define a very specific role that the prompt needs to assume. Then also provide a detailed set of guidelines as to how it should go about categorize the transactions so as to boost the accuracy. Then we also provide examples, both good and bad, from the past transaction classification history. Examples of a good classification are provided to the model, and examples of a bad classification are also provided to the model. And then we provide specific instruction on how the model needs to refuse answering questions that are inappropriate or unethical. So this is how a system prompt that is sent to an LLM is optimized for security. So now let's look at some of the stats over here. What we saw was when we took a foundational model and we just sent a prompt that was not optimized for security, the attack success rate was pretty high, specifically in the prompt injection and the sensitive data disclosure category. On the other hand, after the prompt optimization, the attack success rate reduced dramatically. Let's look at the numbers when we did for a fine-tuned model. In the case of a fine-tuned model, before optimization, we saw high attack success rates. However, after optimization, the attack success rate reduced in one of the categories, or and very marginally in the second one, and then in the third one, it increased. The attack success rate was higher after fine-tuning. So we see how when we are trying to optimize the prompt and sending an optimized prompt to a fine-tuned model, the instructions around security and safety stops being effective. The model fails to understand that. The fine-tuned model fails to understand that. So that is the observation we had in this specific case study. Now, with that, let's look at some of the risk modalities around model misalignment and how to mitigate it. So we have three risk modalities associated with model alignment in the context of fine-tuning. Specifically, when we are fine-tuning a model with explicitly harmful data sets, safety alignment of model is removed upon fine-tuning with such harmful examples. When we are fine-tuning with implicitly harmful data sets, then what we see is model fine-tuned on implicitly harmful data sets are generally jailbroken and willing to fulfill almost any unseen harmful instruction. Whereas in the risk modality 3, and this is the most interesting one, where models are fine-tuned with benign data sets, benign use cases, even then, we see that the safety alignment of the model is compromised. So in the view of these three risk modalities, the first two are mostly in control of the malicious actor, whereas the third one is in the control of the provider of the fine-tuned model. We need to protect the fine-tuned model against all the risk modalities, in the context of all the risk modalities. So let's take a look at the mitigating controls at each phase of the fine-tuning. We start with the pre-fine-tuning phase, then during fine-tuning, and then post-fine-tuning. In the pre-fine-tuning space, the primary risk is training data poisoning and training data leakage. In this phase, we absolutely need to implement data sanitization of the training data to remove potentially harmful data from the training data set, and also remove any PII or other highly sensitive elements from the training data set. And of course, we should be training the model not only on utility data set to boost its accuracy, but also some safety data as well, so that it knows and remembers how to refuse questions that are unethical or impacts the safety of the users of the model. During the fine-tuning stage, the risk is catastrophic forgetting. And in order to address this risk, we need to use the right fine-tuning technique. So at a very high level, there are three primary fine-tuning techniques. We have reinforcement learning, which goes and impacts the model weights in a very selective way. In the second type, which is the direct preference optimization, the model weights are impacted, but it is not nuanced or selective. Whereas in a supervised fine-tuning methodology, it goes and adversely impacts all types of weights associated with the model. So reinforcement learning is the right fine-tuning approach in cases of reasoning models, where it needs to operate within a very complex domain and generate advanced reasoning as its output. In the second bucket, the direct preference optimization, it can be used for simple chat summarization and generating chat messages. Whereas in the third category, where the model weights are adversely getting impacted, we should be using that for classification, where the model is asked to classify elements in the input, user input, based on a predefined canned list of classification values. Post fine-tuning, the risks associated with it is model theft of the fine-tuned model at inference, then membership inference attacks, and training data leakage. And in order to address these risks, we need to implement the right access controls to protect the fine-tuned model. Additionally, access to the fine-tuned model should be rate limited. Then the fine-tuned model should be tested thoroughly for safety and utility before actually deploying it to production. The fine-tuned model at inference, its behavior needs to continuously be audited to measure any drift from its operating model. So with that, we want to conclude. Let's conclude this session by discussing some of the key takeaways. So when you're thinking of adopting fine-tuning for any specific workflow, do explore other alternatives to fine-tuning like RAG. It might offer a comparable boost on accuracy, because using RAG is much simpler than getting the fine-tuning technique right. Of course, implement PII data scrubbing before fine-tuning to address risks of training data leakage from the fine-tuning model at inference. Implement strict access control for the fine-tuned model at inference time. Develop detectors for detecting training data leakage or data poisoning. And this needs to be done both at pre-training and post-training time. The detectors should be running at both these phases. Implement training data sanitization to sanitize the before fine-tuning, and then run the fine-tuning only on sanitized data. This addresses risk of data poisoning. Make sure that you're testing the fine-tuned model thoroughly before deploying it to production. And as a part of this testing, run test cases that are utility-oriented, as well as test cases that test for the adversarial robustness of the fine-tuned model. And in order to inject knowledge around safety and security to the model, make sure that you're mixing utility data and safety data into the training data set, and then fine-tuning the model on that training data set. So with that, I want to conclude my talk. Hope all of you enjoyed it. Thank you.